All right, good morning, everybody. Today we're gonna start the last chapter, and however far we get with it, because we'll meet today, we'll meet next Tuesday, and the Tuesday following. We'll see how far we can get in that time period, because then the week after that is final exams. So I'll give you a chance to catch up everything. So we have 3 more class periods, and to see how many sections we can get done in chapter 10. However far we get on the Tuesday after Thanksgiving, that's as far as we'll do for the course. I'll remove the other ones from the grading scheme. All right, so now we're looking at sequences and series, infinite sequences and series. These are patterns of numbers that can either what we call converge or diverge. And those are important concepts in mathematics. And we'll cover those in class today. And yeah, we'll have these I'll post these also when I finally get a chance to upload everything next week or this weekend. But here we have a whole bunch of examples and definitions and theorems. So that's what we'll go through today. All right. So what exactly is a series or a sequence? A repeated list of numbers that follow a general formula. And are stated on a given domain. The domain could be finite or infinite. So we could say something. We'll in this one we'll use what we'll call indexes or indices. Indices. Those are index numbers. To help localize and count the terms in a sequence or a series, actually. All right, so for example, we have something like this. So here's our index. Our indices usually start at 0 and go on to infinity, or some finite number, usually go on to infinity. So the way this one would be written, so when n is 1, remember, it's a list, it's a sequence, or a sequence of numbers. So that's the first one. N is 2, N is 3, N plus 1. Go always to infinity if you want to. So remember, the n are the counters. So this is sort of like our f of x. Our x would be 1, 2, 3, 4, or dot, 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 n, dot, 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 infinity. So these are our x's. These are our f of x's. Here's another example. B sub n. n plus 1. We know that n cannot start with 0 in this sequence because you can't have divided by 0. So we'll begin. This is my n, or actually my x, my domain. When x is 1, when x is 2, 3, 4, 5. Let's look what happens here. So we have negative 1, 1 plus 1 times 1 over 1. Negative 1, 2 plus 1, 1 over 2. Negative 1, 3 plus 1, 1 over 3. Negative 1, 4 plus 1, 1 over 4. And the last one, negative 1, 5 plus 1, 1 over 5. And it keeps on going from there. So what this one's going to have is negative 1 plus 1 is 2. Negative 1 squared is 1. 1 over 1, so that's 1. Negative 1 to the third power is negative 1. Negative 1 times 1/2 is negative 1/2. Negative 1 to the fourth is a positive 1, so that's a positive 1/3. Negative 1 to the fifth is a negative 1, so it's negative 1/4. 5 plus 1 is 6. Negative 1 to the 6 is 1, so it's positive 1/5. Notice we go from positive, negative, positive, negative, positive, negative. So this is what we call an alternating sequence or alternating series. It alternates between positive and negative. And it keeps on going. N minus 1 over 1. Again, when n equals 1, 2, 3, 4, 5. C sub n. This is 1 minus 1 is 0 over 1, so it's 0. 2 minus 1 so over n, I'm sorry, over n. So it's 1 minus 0 over 1 is 0. 2 minus 1 is 2 over 1 is 1/2. 3 minus 1 is 2 over 3. 3 over 4. 4 over 5, and it keeps on going. N minus 1 over n. And it keeps on going after that. My screen just cancels out. Let me fix my screen again. And we have one more. D sub n is negative 1, n plus 1. N equals 1, 2, 3, 5, and so on and so forth. So D sub n is negative 1, 1 plus 1, negative 1, 2 plus 1, negative 1, 3 plus 1, negative 1, 4 plus 1, negative 1, 5 plus 1, and so on and so forth. So this one will be negative 1 to the power 2 is positive 1. Negative 1 to the power 3 is negative 1. Negative 1 is a positive, so it's just alternating again. So Yeah, this is an infinite series because it doesn't end. They never put a stop to it. We can also write it, this is this last one, because we're looking at a sequence. It's a series of numbers that has this formula, -1, n plus 1. N begins at 1 and goes to infinity. If you notice, this is very similar to the summation symbol. The only difference is this is just listing the sequence of numbers. This is adding the sequence of numbers. So if we look at this last formula, this one, the sequence is 1, -1, 1, -1, blah, blah, blah. This one, the summation would be 1 plus -1 plus 1 plus -1. So these are always cancel, so it equals 0. All right. And graphically, we can look at these things. Because these are our numbers on our list. This is the x values. So if we're going to graph it, this x-axis is actually our n. So when n is 1, n is 2, 3, 4, 5, and so on and so forth. These are my outputs. So we have 1 and -1. So when n is 1, we get positive 1. When n is 1 is 1. When n is 2, we get -1. When n is 3, it's positive. When n is 4, is negative. And it's, so we see that it's a pattern that's going up and down, up and down, up and down, up and down. So that's graphically what we're doing. These graphs are going to be what are interesting to us because that's going to tell us whether we are converging or diverging, depending on what's happening with the graph. All right, so that's what we're looking at there. So as I said, it tells us whether it's converging or diverging. Now, what's the difference? Let's talk about convergence versus divergence. Let's see if I included that. That is on your example sheet. I even have the definition here. So let's look at what this is really talking about. Well, we're always looking at a sequence. So the sequence, whatever it is, converges to a number L if for every positive number epsilon, there corresponds an integer n such that this is reminiscent of the absolute epsilon delta proof in calculus 1. The absolute value of a sub n minus L is less than epsilon whenever that occurs. again, that is very similar to the f of x minus L is less than epsilon whenever x minus C is less than delta. It's very similar to that concept. So it diverges if a number L to a number L, if for every positive number epsilon, there corresponds an integer n such as this is true. It diverges if there is no such number L. So that's the definition of it. Any sequence converges to a number L if for every epsilon there corresponds an integer n such that this is true. The absolute value of the sequence minus the limit, or so the value it's approaching is less than epsilon, whenever some number n is greater than that integer it's coming to. Let's see how we write that. If the sequence A converges to L, then we write it the limit as we're looking at n, as n goes to infinity of our sequence equals L. Basically, it's saying that A sub n goes to L. So the L is the limit. All right. So that's what we're going to be looking at. Let's look at in our example sheet. So let's look at our first example. Show that limit of 1 over n as n goes to infinity goes to 0. Limit of k as n goes to infinity stays at k. K is a constant. And then we'll look at example 2 in a second. Example 1. Let's look at this one. A. The limit as n approaches infinity of 1 over n goes to 0. Okay, we can see this algebraically because when n is 1, we get 1 over 1. When n is 2, when n is 3, when n is 100, the number's getting smaller, 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 smaller. So as it gets smaller, this graph eventually always goes down to eventually 0. That's what. But now let's look at using the epsilon delta type proof. So we're using A sub n minus L is less than some epsilon whenever we have n is greater than n. So this is our A sub n. This is our L. So 1 over n minus 0 is 1 over n. So we don't need the absolute value because we're only looking at positive n's. So what is our value for epsilon? I mean, this is like for our n, to find n, multiply n to both sides. 1 equals epsilon times n. So our n is 1 over epsilon. So what this says, according to this, so this number, 1 over epsilon, is greater than n. Which holds for okay, but that says this. Okay, yeah. So n is that. N is 1 over epsilon. So if n is greater than 1 over epsilon, then it is true. In other words, so this part exists. This is 1 over epsilon. Epsilon's any number. So this number is less than epsilon. And epsilon, 1 over epsilon is what the n is. Our limit is 0. So since this is true and this is true, that means this has to be our limit. Then 0 is our limit. Yeah, it's just, I mean, there's no numbers there, but this says, that's all it says is since these are all true, as long as n is bigger than n, and it's got to be because epsilon, 1 over epsilon is what n equals, and the bigger epsilon begets, the smaller this whole number comes. So this has to be smaller. So eventually that's goes to the limit point. The limit of a constant as n goes to infinity equals the constant itself. Okay, so we have our a sub n minus L is less than epsilon. So we have k minus k is less than epsilon. That's true. So since k is 0, then epsilon has to be positive. That means these have to be positive. Yes. K minus 0. That means epsilon can be any value. So that means any integer. So now we have to get n. Since there is no n, there is no n, it's a constant. Okay, so that means if there is no n, that's 0. That means capital N is negative. But if capital N is positive, then this will be true. Yeah. So for any n greater than 0, the limit of k equals k as n goes to infinity. Like functions of numbers. Okay, let's look at this next one. Example 2. Show that the sequence -1, -1, -1, -1 diverges. Remember, it diverges if it doesn't have a limit value. Example 2. 1, -1, 1, -1, 1, -1, which we figured out that's mathematically, if we look at this thing, if we try to, well, first off, if we did the limit of this function, does it equal L? No, because it's either 1 or -1. So no single L exists. That's where I see it. Because in order to be convergent, this limit has to exist. If this doesn't exist, then what we're looking at here is our value. It could be plus or minus L. So we go from -1 to +1. So let's pick a number between there. No, we can't use 0, so we use a half. There's not much more to prove because epsilon could be positive or negative, but it can't be negative because it's got to be greater than absolute value. So we got to shift it over. So make this into positive. We add 1. So we add 1 to make it positive. Now within that range. But because our -1 and +1 changes, it violates that, so it doesn't exist. I don't know how we're supposed to show that. So this is no single L exists, so it diverges. All right, then, okay, so then if we look at another example, we know that any rational function the limit of that as n or as x goes to infinity, 1 over n, as n goes to infinity, this one converges to 0. Because the bigger the bottom gets, the smaller, so it converges to 0. Same with the radical. So this one, if we look at that, it goes radical 1, radical 2, radical 3. So this goes from 1 to 2. So it increases. It's an increasing function. So it diverges to infinity. And that's the next one. So if it diverges to infinity, if for every number m, there is an integer n such that for all n larger than n, a sub n is greater than m. So no matter what m is, if there's any number, integer n, if I find a little n that's larger than n, so I have this, so m, a sub n is larger than some value m, it keeps on getting larger and larger and larger, it doesn't stop. So we can write this, what we're looking at here, this defines a limit. So we're looking at the limit as n goes to infinity of our value a sub n. It keeps on getting bigger and bigger and bigger, it goes to infinity. Or we can write it a sub n goes to infinity. Yeah, so that, if we look at e function there, looks like that, it goes to infinity. What's the, we look at 1 over x. No. So we want it going to infinity and negative infinity. Let's look at that example. If a sub n equals negative n plus 1. So a sub n would be negative 1 to the power 2 is 1. Negative 2 to the power 3 is negative 2. Negative 3 to the power 4 is 81. So this one diverges because it goes from at 1, it's 1, then at 2, then at 81, then it keeps on going. So it keeps on, it's going to keep on going higher and higher. So basically, the limit as n goes to infinity of a sub n goes to positive infinity, and we can go the other direction. for the function b sub n, we have two different directions. So this is diverges to infinity. This is diverges to negative infinity. Because basically all I was saying here is it diverges if it doesn't go to a limit, it goes to infinity, whether positive or negative. Okay. Let's look at the algebra of sequencing. Limits of sequences. So we have this is a theorem where a sub n and b sub n are sequences of real numbers. Then we have the sum rule that says the limit as n goes to infinity of a sub n plus b sub n equals the same thing as a plus b. These are the limit values. So the limit of a sub n goes to a, and the limit of b sub n goes to b. So if I had the sum of two, these are very similar to what we did in calculus 1, when we did the limits. So then we have the sum, now we have a difference. The limit of a sub n minus b sub n equals the limit value of a minus the limit value of b. Because what would happen here, what's really happening here is this. Is we have a summation here, then we could break these up into the limit as n goes to infinity of a sub n, the limit as n goes to infinity of b sub n, this limit is a, this limit is b. Same thing here, limit of a minus limit of b equals a minus b. What if we had a constant multiple? Limit as n goes to infinity of some constant times a sub n. Since it's a constant, I can factor it out. The limit of a sub n is a. We'll look at the product and the quotient. The product rule, as n goes to infinity, is a sub n times b sub n. The limit of a sub n times the limit of b sub n equals a times b. And the last one, we have the quotient rule. The limit as n approaches a sub n over b sub n, as long as b sub n is not equal to 0, we have the limit of a sub n over the limit of b sub n, which is a over b, as long as b does not equal 0. All right, let's look at the next example. Example 3. By combining theorem 1 with the limits of example 1, find these. Right? Example 3. The limit as n approaches infinity of negative 1 over n. This negative that's a negative, it goes out in front. So we have negative. The limit as this goes to infinity, this one goes to 0. That's 0. Number 2 says limit as n approaches infinity of n minus 1 over n. All right, with this one, I could split these up. I could do n over n minus 1 over n. So the limit of 1 minus the limit of 1 over n. The limit of a constant is a constant. We learned this 1 over n goes to 0, so the answer is 1. The limit as n goes to infinity of 5 over n squared. Yeah, we have the constant times 1 over n squared. One over n times 1 over n. So it's the limit of 1 over n times the limit as n goes to infinity of 1 over n. This one goes to 0. This one goes to 0. So the whole thing goes to 0. And the last one, b, is the limit as n approaches infinity, 4 minus 7 n to the 6th over n to the 6 plus 3. With this type of equation, if we divide each of the terms by the largest denominator, or largest exponent. So we have 4 over n to the 6, 7 n to the 6 divided by n to the 6th, n to the 6 divided by n to the 6th, 3 divided by n to the 6. and sixes cancel, and the sixes cancel. Okay, so I'll do it the long way. Plus 3n to the 6, 4n to the 6 minus 7. Six minus limit as n goes to infinity of 7. I'm just using all the rules. I mean, we take there was a much easier shortcut. So limit as goes n goes to infinity. This one goes to 0. This one goes to 7. Constant, so it goes to 1. This one goes to 0. So it's -7. Which is why we divided by the LCD, the leading term, I should say. Because if we do that, then it's much easier for us to simplify out these terms. We did that in algebra. You do it whenever you uh, look for horizontal asymptotes. Oh yeah, back to another one here. We have, what if we have a diverging or converging sequence of numbers that are non-zero multiples of each other? So we're looking for is if we had something like this, if it was alternating from, let's say, going from here to here to here to here to here to here. So what if our graph is looking like this? If we know these two sequences, because we know they both converge to 0. If there's another sequence inside there, then we can use the same one we used in calculus 1 to prove sine x over x is 1. We can use the sandwich theorem that says that if here's a sub n, here's b sub n. If we can find a sequence b sub n, then this other one, c sub n, is inside there somewhere. So for each of the values, so if this one is bigger than this one, and we know that for sure, they both converge. So by the sandwich theorem, since b sub n converges and a sub n converges, then c sub n has to converge. So let's look at theorem 2, the sandwich theorem. Of sequences. Let a sub n, b sub n, and c sub n these sequences. Okay, so of real numbers. For this example, if we know that a sub n is less than b sub n is less than c sub n, for all n beyond some value n, and if the limits of these, the limit as n goes to infinity of a sub n is equal to the limit of c sub n, and they both go to some limits, like our graph showed earlier. Their limit in this case is 0. So a sub n, c sub n. Since they're both converging to 0, then b sub n must also converge to that same limit. Now, that's if we found a and if we knew a and c, then we can figure out b. So what we're looking for is two functions surrounding another one. We could look at another way, that if we knew that b sub n was less than c sub n, that we can take also. If we knew this, then by taking the negative of that, we have this, and we use the squeeze theorem again. If this converges and this converges, this one has to converge. And these converge to the same negative Cn. The limit of Cn has to equal the limit of positive Cn. Therefore, the limit of Bn has to be the same limit. That's what it's saying. All right. So let's look at our next example. Example 4. Okay, it says, since 1 over n goes to 0, then we know the following. Cosine n over n also goes to 0. Because negative 1 over n cosine n over n. So since this goes to 0, that goes to 0. That means this has to go to 0. The next one is 1 over 2 to the power n. We're saying that one converges to 0 as well. Now, the basic rule also, we do it algebraically. As long as n goes to infinity, this number here gets bigger and bigger and bigger. If the bigger number is on the bottom, then it goes to 0. But we're trying to use our theorems here. This number can never be negative, so we're stuck with 0. Over that. Well, we know this one, the limit of this one is 0. We know the limit of this one is 0. And since it's between there, this limit here has to be 0 as well. Which is that? Where's the third one? Negative 1 to the power n times 1 over n. This converges to 0 as well. But all this one does is oscillate between positive and negative. This one, so we're looking at what this graph would look like, would be positive and negative, and it just keeps on getting smaller, smaller. Okay, this looks like that graph there. So we can use negative 1 over n and positive 1 over n. So there's, again, this one here oscillates between positive and negative. So that means these are going to be equal. The limit of this one we know is 0. The limit of this one is 0. Therefore, the limit of this one has to be 0. If the absolute value of a sub n goes to 0, then the function itself, the sequence itself, has to go to 0. Okay, this is the condition. This is the premise. If this is true, then this is true. So we're going to look at if that one. We'll use a sandwich theorem there, since we know this. So since that goes to 0, the negative of it goes to 0, then this one has to go to 0 as well. That's pretty straightforward. Let's look at example 5. So far, I hope everything's going well. Example 5. Show that n plus 1 over n goes to 1. All right, so it just says show that it goes to 1. Oh. What's the rest of the instructions on that one? Oh, I cut it off. All right, let's look at this. What do we know about n plus 1 over n? First off, since inside there, it has to be greater than 0. Because you can't have a negative inside there. N over n plus 1 over n. As n goes to infinity, this becomes 1. This one goes to 0. So because the inside goes to 1, the limit of that goes to 1 also. Sample 6. The sequence 1 over n converges to 0. We know that. By taking 1 over n, f of x equals 2x, and limiting to 0, theorem 3 says, oh, I didn't talk about 3. Let's talk about theorem 3 first. Continuous function theorem for sequences. It says, I'm just reading off it. Let A sub n be a sequence of real numbers now. If A sub n has a limit L, and also if f is a function, is a continuous function at that limit, and f is defined at all x's or a sub n's, then the function of the sequence approaches the limit of the function. So the continuous function, so if the sequence A be a sequence of real numbers, yeah. If the limit of the sequence as n goes to infinity approaches L as n approaches infinity, and if f is a continuous function at L, and f is defined on all a sub n, which has to be true, because if this is the limit, then all the points have to exist also, has to be continuous, then the function of the sequence tends to the function of the limit. Okay, let's put that into words. Put the words into action. So here's our example 6. Now it makes more sense. Okay, the sequence 1 over n converges to 0. We let a sub n equal 1 over n, and f of x equals 2 to the power x, and the limit equals 0, because that's what that one goes to. The limit is 0. Then theorem 3 says 2 to the power x, 1 over n, is equal to the function of 1 over n, because that's our x value, and it approaches the function of the limit. So the function is 2 of x. In place of x, I put that. So 2 to the power 1/2 goes to, well, the limit is, well, the function of the limit is 0. F of 0, which means 2 to the 0. Okay, so 2 to the 1/2 power goes to 1. So a sub n 2, 1 over n converges to 1. Okay, that makes, so our theorem said this: f of a sub n f of L. The function we have is 2x. So it's going to be 2 to the power a sub n. I changed my x value to a sub n. This becomes 2 to the power L. A sub n is 1 to the power n. L is 0. So 2 to the power 1 over n approaches the... That makes a lot more sense. Okay. Okay, so let's see if there's any more examples here. That's 6 and 7. Oh, yes. Using L'Hopital's rule. Remember, L'Hopital's in Calculus 1, that if you had a function that was 0 over 0, or infinity over infinity, or 0 over infinity, any of those combinations, we could take the derivative of it. In other words, if this limit was going to something undefined, we could take the derivative of the top and the bottom and try it again. And keep on doing it till it's no longer either 0 over 0, or one of the top and bottom becomes a value. So let's look at this theorem. Suppose f of x is defined for all x's greater than the initial n value, and that the sequence a sub n is a sequence of real numbers such that a sub n equals f sub n for some n bigger than the initial n. Then we'll know that the limit of our a sub n as n goes to infinity has a limit. When the limit as n goes to infinity of the function has limit. Yeah, since this is true, if the limit of a sub n goes to infinity, or as n goes to infinity is a limit, then this one has to have a limit. Yeah. Let's look at example 7. Show that the limit as n goes to infinity of ln n over n equals 0. Okay, so using L'Hopital's rule says the derivatives of top and bottom. So the derivative of ln x, because if you look at the top and bottom, as n goes to infinity, ln goes to infinity is infinity over infinity. We can't do anything, so we can take the derivative of top and bottom according to L'Hopital's rule. The derivative of limit n is 1 over n. The derivative of n is 1. So the derivative of 1 over n is 0. That's exactly what we're trying to prove using L'Hopital's rule. Again, L'Hopital's rule is if you have an indefinite integral or 0 over 0 undefined, then you keep on taking the derivative of top and bottom separately and try the limit again until either one of those or both of them are no longer zeros or infinities. Does the sequent whose nth term is n plus 1 and minus 1 to the power n, if so, find the limit of a sub n. Okay. So does this function converge? All right, so in order for it to converge, we have to make sure that it goes to some value. Okay, so how are we going to approach this? We have an exponent there, it's an n. We have to get rid of that. So the only way we get rid of that, we take the natural log or the log base 10 of both sides. That's the only way we can get rid of this top equation here, because according to the rules of exponents or logs, you can't have exponents. That comes in front. Okay, because now since we have no more exponents, we can now look at this as the limits of these. So the limit as n goes to infinity, the limit as n goes to infinity of this. The limit of ln as, well, we'll basically look at this. So the limit as goes to infinity of ln a sub n this becomes the limit of n ln n plus 1 n minus 1 Okay, we can't use L'Hopital's rule just yet. Because this equation goes to 1. And to use L'Hopital's rule, we have to have a fraction. That's where that one comes in. Okay. So the limit as n, the ln of that one. You can't put, so that's 1 over n on the bottom. So as n goes to infinity, this one goes to 0. And that one goes to infinity, actually. Because this increases by 1, this decreases by 1, but it's still undefined. So now we take the derivatives. The derivative of the top, derivative ln, is du over u. Over u. I could look at this ln n plus 1, which is 1 over n plus 1, 1 over n minus 1. There's ln n minus 1. The derivative is 1 over n plus 1 minus 1 over n minus 1. It'll be n minus 1 minus n plus 1 over n plus 1 n minus 1. So n minus 1, n minus n minus 1 makes it 2 n minus 1. No, the n minus n cancel. So we have -1 minus 1 is -2. On the bottom, n plus 1, n minus 1 is n squared minus 1. So the derivative of the top is -2 n squared minus 1. The derivative of the bottom is n to the power -1. So it becomes -1 n to the -2. So it's -1 n squared. Negatives cancel. 2 over n squared minus 1, and the flip of that one, n squared over 1. Now, as n goes to infinity, well, we'll read another page. We have the limit as n approaches infinity of 2n squared over n squared minus 1. Divide everybody by n squared. So the top we get 2. That becomes 1 minus 1 over n squared. As n goes to infinity, this one goes to 0. We have our limit equals 2. So, okay, all this, left-hand side, we said ln of a sub n equals 2, or approaches 2, because this is our limit. Okay. Okay, we're getting to the pretty close to the end here. Let's see, now we have commonly occurring limits. Theorem 5. The following converge to the limits. N goes to infinity of ln n over n equals 0. Limit as n goes to infinity of the nth root of n goes to 1. Limit as n goes to infinity of x to the power 1 over n goes to 1. The power n goes to 0. As long as the absolute value of x is less than 1. In other words, the absolute value of x is less than 1, so it means it's a fraction. If it's a fraction, then it's the exponential function is 1 over, let's say 1 over 2 over, the graph looks like this. So it's a decreasing function. It goes to 0. The limit as n approaches infinity of 1 plus x over n to the power n is e to the power x for any x. X to the power n over x factorial equals 0. This is read x factorial. All it means is multiply everything from x down to 1. So 3 factorial would be 3 times 2 times 1. 5 factorial would be 5 times 4 times 3 times 2 times 1. It's 20 times 3 is 60, is 120. So that's what the factorials are all about. So in the future, because of this theorem, if we see any type of these forms, we don't have to do any work, just state this by the theorem. Hey. Thank you, theorem. So, example 9. Example 9. This one. These are examples of limit 5. So A says the ln of n squared over n. Okay, you can't have an exponent, so it's 2 ln n over n. By the theorem we just had, this goes to 0. Goes 0. N squared. So this one is written as 2 over n. We can rewrite this as that. And from the theorem, wherever it was, whenever you have x to the power n to the 1/2, that's 1. So it goes to 1. Again, these are all just statements. These are straight from the theorem. N to the power 3n, which is 3n to the power 1 over n, 3 to the power 1 over n, n to the power 1 over n, distribute. According to the theorem, anything to the power 1 over n goes to 1. So this one goes to 1, this one goes to 1, it goes to 1. B negative 1 over 2 to the power n becomes negative 1 to the power n, negative 1 to the power n, 1 to the power n, 2 to the power n, negative 1 to the power n. Anything to 1 to anything is 1 over 2n. This between positive and negative, but this one keeps on getting smaller. So this one goes to 0. E n minus 2 over n to the power n, n over n, 2 over n. Whenever we have a monomial on the bottom, we have 1 minus 2 over n. We say, because in this property is number, this one, 1 plus x over n to the power n is e to the power x. So this becomes 1 plus negative 2 over n to the power n. So this one leads to e to the power negative 2. Because this used to be a negative 1, positive 1. And F. 100 to the power n over n factorial. Well, that's just a stroke. Anything to the power n over n factorial is 1. Anything to the power n over n factorial is 0. I put one there? No, 0. So those are just straightforward. Okay. The next topic in this section, this first section, recursive definitions. Okay, so let's look at this. So up until now, we've done all the calculations directly with respect to the limits and the n. But sometimes our sequences occur recursively. When they do, sequence are sometimes defined recursively by giving two things. One, the values of the initial term, and two, a rule. This rule is called the recursive formula. The rule for calculating any subsequent term from preceding terms. In other words, if you give me the second term, I can tell you the fourth term. If you give me the fifth term, I can tell you the 10th term. That's what we'll look at here in example 10. If a equals 1 and a sub n equals a n minus 1 plus 1 for all n greater than 1, so we know that when a1 is 1. So here, if a1, then this is 1 minus 1 plus 1. We don't have an a0, so it equals 1. True. So far, so good. a2. a2 minus 1 plus 1. So it's a1 plus 1. a1 we determined was 1. And then a3, 3 minus 1 plus 1. So this is a sub 2 plus 1. Well, a sub 2 is 2. So that's what it's saying recursively. It's iterative. It keeps on going step by step by step. That's A. Let's look at B. If A equals 1 and A sub n equals n times n minus 1 for all n greater than 1. So we start with A1 equals that. Because if you look at this, this is A1 equals 1 times A1 minus 1. 1 times a sub 0. So it has to be greater than 1. So it's 1. A sub 2. N is 2, so it's 2 times 2 minus 1, which is 2 times A1, 2 times 1, which is 2. A3. 3 times A3 minus 1. 3 times A sub 2. A sub 2 was 2, so that equals 6. Let's do one more. A4 is 4 times A sub 4 minus 1 equals 4 times A3. A3 plus 6. 4 times 6 is 24. And we keep on going from there. Let's look at another one. A equals 1. A2 equals 1. AN plus 1 equals AN plus AN minus 1 for all n greater than equal to 2. Because yeah, we already have 1 and 2, so we start with our n's greater than 2. So we look at A sub 3. Well, so let's look at. So A sub 3 is A2 plus 1. So we got, since this is 2, we have A sub 2 plus 2 minus 1. A sub 2 plus A1. So we have 1 plus 1. So A3 equals 2. A3 plus 1, which is our A4, which is n is 3, so it's 3 plus 3 minus 1. A sub 3 plus A2, so it's 2 plus 1 equals 3. A5 is A4 plus 1. So it's A4 plus A4 minus 1. A4 plus A3. 3 plus 2 equals 5. And keep on going from there. Let's see what else we got. Oh, the last topic. Bounded monotonic sequences. Bounded. That means it has an upper or lower bound. Monotonic. Monotonic simply means that it's either increasing or decreasing. Can't be both. It can't be oscillating. So opposite of monotonic is oscillating. So here are our definitions. A sequence is bounded from above if there exists a number m such that a sub n is less than m for all n. We'll say that m is an upper bound for the sequence. Right? And then we have another definition here, along with upper bounds. So we're saying that if m is an upper bound for the sequence a sub n, but it has no number less than m, we say that it's an upper bound for a sub n, where m is the least upper bound. For the sequence. Again, if m is the upper bound, but no numbers are less than m, then it's the least upper bound. Conversely, let's look at bounded below. The sequence a sub n is bounded from below if there is a number m, lowercase m, such that a sub n is greater than all the m for all n. So all of these a sub n sequence numbers are bigger than m. The number m is a lower bound for the sequence let's say, no, I say if m is a lower bound for the sequence, but no number greater than m is a lower bound. For a sub n, then m is the greatest lower bound for the sequence. Basically, all it's saying is if we have a sequence of numbers like that, and here's our capital M, and here's our minuscule m. This is our upper bound, this is our lower bound. So if the entire sequence, if there's no number higher than that, or no number lower than that, then that's the least upper bound. The lower bound, if there's no number higher than there that fits, then that's the the greatest lower bound. So that's by definition. And also by definition, if you'd see this, we know that convergent sequences have to be bounded. That just goes common sense, because if it converges, then it's either going to be a constant term, which is a straight line, or if it's an oscillating or decreasing function like 1 over x, if it looks like this, there are upper and lower bounds. Oh, and there they are. Okay, so now we look at this more definitions here. A sequence is non-decreasing if the sequence, the lower values, if it's an increasing sequence for all n. Notice what that means is you have a sub 1, which is less than a sub 2, which is less than a sub 3, which is less than a sub n plus 1, which is less than a n sub 2, and so on and so forth. So that's non-decreasing because it's an increasing function. It's getting bigger. A sequence a sub n is non-increasing if a sub n is bigger than all the ones after that. So they're just saying that a sub 1 is bigger than a sub 2, is bigger than a sub 3, is bigger than a sub n, is bigger than a sub n plus 1. And finally, the sequence a sub n is monotonic if it is either non-decreasing or non-increasing. In other words, if it's an increasing or decreasing function. Let's look at the sequence. 1, 2, 3. It's getting bigger, so this is non-decreasing. B, 1/2, 2/3, 3/4, n over n plus 1. 1/2, 2/3 is bigger, so it's always increasing. It's non-decreasing. We have 1, 1/2, 1/4, 1/8, 1/2 to the power n. So these are getting smaller. So this is non-increasing. Three, 3, 3. It's both non-increasing and non-decreasing. And the last one. 1, -1, 1, -1. -1 power n. It's neither, this is increasing and decreasing, therefore it's non-monotonic. These are all monotonic because they're either non-decreasing or non-increasing. But this last one is neither increasing or decreasing, so it's non-monotonic. And as the theorem states, the theorem here says, if a sequent is both bounded and monotonic, then the sequent converges. If the sequence is both bounded and monotonic, meaning it has an upper and lower bound, and it's monotonic, means either non-increasing or non-decreasing, then it converges. That's the theorem. All right. So that does it for this section. Unfortunately, this was the longest section of this chapter. That means all the other ones are, this one had like 10 or 12 pages to it because it just introduced all the concepts of sequences and series. The rest of the sections in this chapter deal with 5 or 6 pages. So we'll start doing 2 or 3 sections per class. Next Tuesday, we'll do sections 2 and 3. The Tuesday afterwards, we'll do 4 and 5. And then we'll see about if we're going to continue any further on Thursday, because it only gives us a week to finish everything. So that's it for this week. We'll see you guys next Tuesday, and we'll continue from there. All right, have a great weekend.